So let's talk about one of the most fundamental concepts in statistics, namely that of a random sample. Broadly speaking, statistics is about data. It's about collecting, analyzing, and presenting data. So here, for example, I have some data consisting of 10 different x values, which I call x1 through x10. So what we would like to do now is to better understand the process that has generated this data. Let's say that this data comes from me tossing a dice 10 times and recording the result. So in the first observation, I tossed the dice and I got a 3. So using probability theory, we can think of this as an experiment where I toss a dice, I define a random variable called x1 whose range is, and if I feel that I'm dealing with a fair die, I could describe a probability distribution function by assuming that each outcome is equally likely and specify that the probability of each possible outcome is 1 by 6. And then I simply think about small x1, the number that we recorded in the table, as a drawing, as the outcome of the experiment. Well, I can do the same thing for the second observation by specifying a second random variable called R2 with exactly the same range and exactly the same probability distribution function. And I can assume that x1 and x2 are independent random variables. In this case, that makes sense because the result of the first toss will not influence the result of the second toss. Small x2 is then viewed as a drawing from capital X2. I continue in the same manner, so I end up defining 10 random variables from x1 through x10, all of them being mutually independent and all of them being identically distributed, exactly the same distribution as the one I specified for x1. The data that I observe is then 10 drawings, one from each random variable, and that is my data. So when we think about our data in this way, we talk about having a random sample, or sometimes it's just called a sample. And we can define a random sample simply as we have set up an experiment. In my example, the experiment was to toss a dice 10 times. We define a number of random variables, so let's call that number n. So n was 10 in the example above, and we denote them by x1, x2, all the way to xn. The n numbers that these random variables will take after the experiment, small x1 through xn. We also use the word sampling process for the process of collecting the random sample. So when we actually toss the dice 10 times, we are doing a random sampling. I should also mention that sometimes we think of data as simply being drawn from a population. For example, say that you have an urn with black and white balls, and you keep on pulling black and white balls out of that urn, recording the color of each ball, then you will end up with a data set which you can say is drawn from a population. To me, this concept of population is not very useful actually. For example, if you toss a dice n times, it's really hard to think of what the population should be. It's certainly not the numbers 1 through 6, because that would imply that once you've tossed 1, you've used that up and you can't get a 1 again. Some people would say that the population in this case is an infinite number of ones, an infinite number of twos, and so on. But to me, that's kind of a useless concept. So I much rather think of statistics and random sample using the concept of random variables, avoiding the population concept altogether. So let's say now that I have a random sample. I've defined n random variables, and I think of a random sample as n drawings from these random variables. So often what we would like to do in statistics is to draw some conclusions about these random variables. For example, we might be interested in figuring out the expected values of these random variables, or I could have a random sample consisting of n observations on an x variable and n observations on a y variable, and I might be interested in the relationship between the x and the y variables. Well, if I like to know more about these random variables, then it's quite clear that I have to make additional assumptions. I cannot really draw any kind of conclusions about n random variables if all I have is one observation from each of them. One such assumption, which is sometimes reasonable to make, is the assumption IID, which stands for independent and identically distributed. So if I make this assumption, I'm assuming that all the random variables are independent. In the case of tossing a dice, that makes sense because each toss will not affect the other. Assuming identically distributed means that each random variable has the same distribution. Well, as long as I'm using the same die in each toss, that's a reasonable assumption. It's also quite clear that it's not always we can make this assumption. Let's say that I define 10 random variables representing the temperature in 10 consecutive days. Then it's quite clear that I cannot make the independence assumption. If the temperature is unusually high one day, then it's more likely that it'll be high the next day as well. So there is a dependence between the random variables. However, when you can make the IID assumption, then statistical analysis becomes much simpler and you can draw conclusions which you otherwise will not be able to. If you're dealing with an IID sample, such that all these n random variables are independent and identically distributed, well, then they must have the same expected value. Remember, the expected value is calculated from the distribution, or the probability density in the case of a continuous random variable. So if they are the same, the expected value must be the same. And in this case, we can simply denote this common expected value by mu. Similarly, they all have the same variance, and we can denote that by the common symbol sigma square. This is typically the first example that you study in statistics. You start with an IID random sample. Mu is unknown. Sigma square is unknown as well, but let's focus on mu. And you want to use the data to come up with a good guess of mu. Kind of the prototypical statistical problem. Another assumption that's sometimes made in statistics is that we specify the family of distributions for these random variables. So we may say, for example, that x1 follows a normal with expected value mu and variance sigma square, so we don't assume a specific value for mu or sigma square. This is why we say that we've specified a family of distributions. We can make the same assumption on all of them, that this is normal mu sigma square, In this case, it's quite clear that they're identically distributed. And if I would like to also assume that they're independent, then the common notation is the following. x1 dot 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 xn are IIDN mu sigma square. That means that I have n random variables. They're mutually independent. Each one follows a normal distribution with an unknown mu and an unknown sigma square, and so they are identically distributed. The purpose of statistics is then to use the observations to make educated guesses, or estimates as we call it, of mu and sigma square.